Hello and welcome. My name is Mira Kuchibuzo Marcel, and welcome once again to our lecture. So today we are going to be discussing two famous variable stars, and those two famous variable stars are Cepheid variables and all Lyrae stars. Those are the two standard candles we mean the most famous standard candles we have in astronomy. So just a gentle reminder that this lecture is sponsored by the Free Astro Science. So as part of our table of content, I'm going to be introducing variable stars and just general information about variable stars and elaborate stars. Then I'll talk about the instability strip and the HR diagram. Then I'll discuss the kappa mechanism, what is making the variable stars to pulsate. So that's the kappa mechanism. Then I'll give a brief information about the Cepheid variables and the all Lyrae stars. So here are the light curves of the Lyrae stars and the Cepheid variables. So you can see how they pulsate. They inflate rapidly and slowly declines. So that is how they pulsate. Even surface behave that way, but just that the slow decline is more pronounced in a Lyrae. So that is why the light curves like this. So we're going to discuss why they behave this way. So if you look at that diagram, you can see that they slowly expand. Like I said before, they slowly expand, becoming thinner. So you can imagine them. Imagine the situation as a balloon. When you inflate a balloon, it becomes thinner at the surface. So for the star, it becomes thinner and cooler on the surface. And why it declines, why it contracts, it becomes smaller and harder. Okay, and the process repeats. So you can take three things from this. You can take three essentials from what is going on. So in terms of the size changes. So there's a physical change in the size of the star. That means there is a reduction, an increment in the radius. So the radius goes up and down. Okay, that is it. So just take for instance let's take for instance the Cepheids. So let's imagine the size, the radius. Okay, the size to be 100%. Okay, when it contracts by 15%. It becomes 15% smaller. That is 85% than the average size. And when it expands, when it inflates, it becomes 15% higher than the average size. So that is what's going on. 15% below, 15% above. Then in terms of the alloy, if the size is 100%, and when contracts, it contracts by 5 to 10% of its original size. So that means 95% or 90 to 95%. And when it expands, it becomes 105 to 110% of its of their average size. So that is exactly what's happened. So that is a change in the size. That means a physical change in the size. Then in terms of temperature changes, there is also change in the temperature. So for Cepheid variables, if the temperature is the immediate temperature, you say 100%, they can get as cool. They can lose temperature to, they can lose about 5% of their heat, so that it reduces to 95%. And when they contract, they can gain more heat, like extra 3 to 8% of the median temperature. So that is for Cepheids. Then in terms of Lyrae, when they expand, they can lose heat ten, between 5 to 10%. And um when they contract, they can get as hot as 105 to 110% of its medium medium temperature. So if I may want to ask you which one becomes hotter, and which one becomes cooler, I think you can point to you can point to Lyrae. Lyrae becomes hotter and cooler. Okay, so and the process repeats. It repeats all the time. I'm going to discuss why it repeats. So now, look at this is like this is supposed to be our sun, supposed to be our sun, and here is Earth moving in front of it. So, but why is it not behaving this way? Why is it not behaving that way? Like showing that variability. Although the sun shows it a little bit, but not it is not pretty pronounced. So, but let's understand what's going on there. Why is the sun and most stars do not behave that way? It's only a couple of stars that behave that way. So, and that is where the instability strip and internal phases comes in. We're going to be treating that. So, follow me. So here is the instability strip. First of all, here is the Herschel diagram. The Herschel diagram, you're familiar with it? So the Herschel diagram plots the brightness and the vertical axis and the temperature or spectra on the horizontal axis. Okay, so you can here you have hot stars and here you have cooler stars. Okay, now the instability strip is here. All the stars that fall in here are in the instability strip, and these stars are the Cepheids and the Lyrae stars. So you can see them there. So, and those are the ones that pulsate. So you can see that here. Remember, here is the main sequence stars, right? Here's the main sequence, and here is the stars in the instability strip. So, and remember, stars in the main sequence fuse hydrogen into helium, but stars here no longer do that. They no longer fuse hydrogen to helium. Okay, they fuse helium to higher elements. So note that. So there's active helium fusion going around this region, and that is important. That is very important in what we are going to be analyzing later. So now let me come to helium. Helium atom has two electrons, two neutrons, and two protons, right? And it's an inert gas. It doesn't react with any element. Okay, so but under high enough temperature, it can lose one of its electron and to become partially ionized hydrogen ion, just one electron. Okay, but under the condition of the stars, like the core of stars where the temperature is high, they can completely lose those two electrons to become completely ionized helium ions. Okay. Now, one thing about this ionization is that it increases the opacity. So as um, the more it loses electrons, the more opaque it becomes. I mean, opacity means it doesn't allow light to pass through. So you can imagine it as your uh, just something that's like for waterproof. Waterproof does not allow water to pass through. So for light, it is an opaque substance or opaque object does not allow light to pass through. So that is how it works. So completely ionized helium do not allow light to pass through. Okay. So, but partial ones also allow a little bit of light to pass through. Then helium atoms they are just transparent to light. So, this idea is going to play a very big role in the next thing I'm going to be explaining, which is the Kappa mechanism. So, here is the diagram of a star. You know, maybe Cepheid. This thing, what I'm about to explain, also apply to Cepheids and Lyrae stars. So here's the core of a star. Um, the core where the helium fusion takes place. So, and here's the first layer. Here's the second layer. So I'm gonna just use these two layers. Okay. In the in the layer closer to the core, the temperature, because that is where the fusion takes place. The temperature is high enough, and because of the closeness of this layer, all all the helium here are completely ionized, so they are doubly ionized helium. So we call it doubly ionized helium layer, okay, yeah, because of the closeness. And because of that, it becomes very opaque to light. Light does not pass through. And so there's going to be a buildup of pressure, radiation pressure in this zone that is going to overpower the gravitation, the infalling matter, the gravity of the matter. So as that happens, it's going to push out the radiation pressure. It's going to push out the matter, and as it pushes the matter out, they are going to start to gain electrons. They're going to become single ionized until they get to this point. And what happens is that as they are being pushed, they become lesser and lesser opaque, I mean more transparent, so that radiation is going to seep through any escape route. So becomes so the radiation pressure becomes less and less. And so what happens is that when it gets to this layer, most of the helium becomes single ionized. So you call it single ionized helium. So at that point, the pressure has reduced, so gravity gains the upper hand and the layer falls back and the process repeats. So here, that's the couple mechanism. So that's exactly what makes the the star to behave that way. So you can see it when it is blue is when it is contracted, and when it is red is when it expands. So I use this blue color to depict it because in the electromagnetic spectrum, blue represents higher energy and red represents lesser energy, lesser frequency. So that's like the physics behind so physics behind the the variabilities of surface on the Lyrae stars. Now I've explained the instability strip. Now I've understood the instability strip and the couple mechanism, which is the physics behind the variabilities of Cepheid and Lyrae stars. Now let me talk about the Cepheid variable stars. So the Cepheid variable stars are very large stars. They are pretty large, and they are very bright, and they are yellowish in color. So these are super giant stars, very big, massive stars. So that's rhythmically brighten and dim in a predictable cycle. So some of the key characteristics of these Cepheid variables is that they are about 10,000 to 100,000 brighter than the sun. So you can imagine that. Okay, and that is because they are very large. Okay, they are very large. The radius is between 20 to 200 times the sun's radius. So you can imagine that. So 20 times to 200 times the radius of the sun. In terms of mass, they are pretty massive. They are between 4 to 20 solar masses. And in terms of temperature, they are yellowish. The temperature is the yellowish in color. The color is due to their temperature, remember? And that is between 5,000 to 6,000 Kelvin. So that is pretty much similar to the temperature of the sun, but they are far larger and brighter than the sun. Okay, so in terms of their stage, their evolutionary stage, so they are super giants and that have left the main sequence and are now burning helium in their core or shells. So take note of that. So now Cepheids are known by their signature pulsations. Okay, so their pulsation period is between 1 to 100 days. Okay, so that can be divided into two. We have the short Cepheids, short period Cepheids. So these are Cepheids that pulsate within 1 to 5 days. Okay, these kind of sulfates are smaller and less luminous. Then we have the long period sulfates. They pulsate between 20 to 100 days, and they are pretty. These ones are pretty enormous sulfates, that enormous stars, and they are extremely bright stars. Now, the brightness cycle of sulfates are not symmetric, and what I mean by that is that okay, for instance, they brighten up so quickly, okay, they brighten up so quickly, but they fade more slowly. So that is exactly what I mean by that. So that creates these the sawtooth that you saw in this light curve. So they brighten up very rapidly and decline very slowly. So that is why the light curve is this way. That is signature of the pulsar of Cepheids. Now, in terms of where they are found, Cepheids are found, Cepheids are young stars. They are young stars, okay? So they are found primarily in young star populations. So typically in the spiral arms of galaxies, that is why you see a lot of young stars. So galaxies, okay, not just our Milky Way galaxies, other galaxies, including the Milky Way galaxy, they can be found in open clusters and can be found in star-forming regions. And the reason why you find them in this region is because they are massive stars. And massive stars don't live long. Remember, they don't live long. So they only live between tens to hundreds of millions of years. Okay, compared to the sun, sun is not a massive star, which is the sun is which is about 10 billion years. You know, the sun is going to live for 10 billion years, right? So, but these Cepheids, these young stars, just live within few million years. Okay, so they appear where recent star formations occur. So now, Cepheids. Why are Cepheids important? Cepheids are important because they are used as standard candles. They are used as standard candles in astronomy, okay? And we use standard candles to measure distances. So Cepheids obey what we call the period luminosity relation. That is, the longer the period, the brighter the star truly is. So this idea was invented by Henrietta. You can see her here. She came up with this period luminosity relation for variable stars. And she made plots of uh, different variable stars, the luminosity with respect to their precession period, and came up with that relation. So she also did it for our lovely stars, but the lovely stars do not obey period luminosity relation. They obey a different relation, which I'll talk about later. So, so by measuring a Cepheid's period, astronomers can calculate its true luminosity. Okay. So then, if you compare these true luminosities with the observed brightness, then you get the distance. You get a distance. So this makes Cepheids uh, this makes them very essential for measuring distances to nearby galaxies. So if you want to measure distances to nearby galaxies, you look for Cepheids in those galaxies. If you can get a distance to this Cepheid, that is ultimately gives you the average distance to the galaxy. Then we have star forming regions. That we have the scale of the Milky Way galaxy. The size of the Milky Way galaxy. We said this Milky Way galaxy is about 100,000 light years across. And the reason why we were able to deduce that is because of the Cepheids. We could also use the alarm stars, but we can most of the times use the Cepheids. And also the expansion of the universe. When Hubble, discovered that the universe is expanding, he observed Cepheids in galaxies, and that helped him to calculate and came up with the idea that the universe is expanding because the distances expand. So now let's talk about the Lyrae stars. Lyrae stars, on the other hand, are older, smaller, and low mass pulsating stars compared to the Cepheids. They are ancient. The age is typically 10 billion, almost the same age of the universe, 10 billion years old or more, and represent some of the first generations of stars that formed in the Milky Way galaxy and even ultimately in the universe. I think there are population 2 stars, yeah. Population 2 stars. And some of their key characteristics is that in terms of their radius, they are bigger than the sun. They're just 5% the sun's radius, but they are much smaller than Cepheids, okay? But they're bigger than the sun, but much smaller than the Cepheids. Then in terms of mass, they are less massive than the sun. Okay, they are 0.6 to 0.8 the mass of the sun. In terms of luminosity, they are brighter than the sun by 40 to 50%. 40 to 50 times the sun's brightness. Then, in terms of the evolutionary stage, there are horizontal brain stars that have started burning helium in the core. So, in terms of their location, they are found in old environments like in globular clusters in the galactic halo. So this is, I mean, though this is the way this pulsate is exactly how a lot of stars pulsate. Now, in terms of how fast they pulsate, a lot of stars pulsate faster than Cepheid, so they have a shorter periods. The period range between 0.2 to 1 day, so a shorter pulsation period, but many complete full cycle in half a day or even in few hours. And so because they pulsate so rapidly, their light curve show sharp, steep brightness changes. So they are small so that it's the expansion and contraction happen quickly, creating energetic pulses. So if you look at this light curve, see that it rises so rapidly to the maximum, but then it slowly declines. Okay, and they have these usually have this bump in the light curve. So this is how we know. That is how we know. So in terms of where they are found, globular clusters are found in, like I said before, they are found in globular. So alarming stars are found in globular clusters. Okay, they're found in globular clusters and the Milky Way halo, and those dwarf galaxies, orbiting our Milky Way galaxy. Now, why that is important is because alarming stars can help us to measure distances to these global clusters. If we want to measure the distance to these global clusters, we look for large stars. So we can also use them to measure distances across the galactic halo and distance to nearby dwarf galaxies. So they are very important. So I did an extensive research on large stars, and one of them is BNCVN. I used, no, remember what I just told you about measuring distances? That Cepheids follow the period luminosity relation, but a lot of stars follow what we call period luminosity metallicity relation. So, if you want to understand how that works, I will invite you to read my paper, um, B and CVN distance determination using that relation. If you want to get the paper, you can just simply scan the barcode. Just take you directly to the paper. So I'm going to give you a little bit of time to scan it. And thank you so much for joining us.